The lab is so hard.
I'm trying to lab, but like,
All right, we're gonna start. That's not even perfect English. So today we're going to be discussing eigenvalues and eigenvectors. So far we have discussed stochastic matrices, a lot of them in the context of populations. And what we were looking for is where a steady state equilibrium was reached, and we were finding what that equilibrium would be and defining the stochastic matrices. So that is directly related to eigenvectors and eigenvalues. This is an example of an eigenvector and an eigenvalue in action, because the eigenvector would be x, and I believe eigen means own. I think we talked about that already.
Alex?
And then here are our eigenvectors.
Not really confident.
And for this one is our eigenvalue. So it doesn't always have to be 1. 1 helps you reach a steady state, because when you multiply the stochastic matrix times the population vector, but in this setting it's called, or in a more general setting, it's called the eigenvector, it's the same as multiplying by 1. Okay? So essentially, multiplying by this big old stochastic matrix is the same as doing a scalar multiplication by 1 in a steady state matrix, but in every other eigenvector eigenvalue situation, this doesn't have to be 1. So the eigenvalue is 1 with our Markov chains, but it can be any value. So essentially, we're looking at how multiplying by a matrix would be the same as multiplying by a scalar value for that particular eigenvector. So when you're generalizing the entire situation, we use the lambda to denote the eigenvalue, and then our eigenvector is still x. Yeah, so here I wrote it down because I forget sometimes. So the prefix eigen is German, and it's self, or unique, or particular to, or belonging to. So it's the eigen, so the vector that reflects upon itself or any eigenvalue. Those are all of them. Yeah.
So like for the original stochastic matrix case, the eigenvector is just like x to x to x to, right?
Right, and it's the population vector. Like for our rainy and shiny situation, we started with the eigen being 1/3, 1/3, 1/3, and we saw what it did over time, given it's never nice 2 days in a row, all of those situations. So it was that population factor, which excellent, excellent. Other questions? So this is where we kind of relate it to all the things we've been doing, the concept of eigenvectors and eigenvalues. So here we have an eigenvalue, which is lambda, which is a scalar quantity. And this is a very important little sentence in here. If there is a non-trivial solution of the equation ax equals lambda x, then there is an eigenvector corresponding to that eigenvalue. So you need to have a non-trivial solution to this homogeneous equation in order for there to be an eigenvector that has a corresponding eigenvalue. If you just get the trivial solution, that means the only thing that works is when x is 0, when we solve for 0 in the equation to create a homogeneous equation. But if only 0 works as your eigenvector, there is no eigenvector, because that's the trivial solution. When you solve for the set of all solutions, it's the null space of that matrix, because the definition of null space are the vectors that solve the homogeneous equation, and that is what this is. So this is the connection to null space from last chapter. So we're finding the null space of A minus lambda A, and we get that by basically subtracting the lambda x from both sides and then solving by factoring out the x. So that's how we get that homogeneous equation. Question so far? So you're looking for non-trivial solutions to the equation x minus lambda, or sorry, A minus lambda x equals 0. Where lambda is the eigenvalue and x is the eigenvector for any defined A. And again, on your lab, you won't be able to use any books, okay, or computers, just your notes and your homework.
Is it in class?
It is in class unless, yeah, it's in class. It's usually in class, you have access to everything.
Is it like a work or?
It's a lab, so you're going to be paired with one of your classmates.
Do we get a pickup partner?
No. Okay. So,
Well, I don't know, maybe if it lasts a while, we got a pickup partner. I'm not sure.
that would be a non-graded last for that, not a graded last for that. So the subspace that is created by the null space is called the eigenspace of A corresponding to that particular eigenvalue. And it will always include the zero vector because the zero vector is the trivial solution of that homogeneous equation. But then if they have anything else, and then you have eigenvectors and eigenvalues. Because the zero vector will always solve the homogeneous equation. Okay.
So, like, what's the difference between subspace and eigenspace?
So subspace is a general term, but the eigenspace is specifically the null space of the equation ax, a minus lambda times x equals 0.
Okay.
So it's all of the solutions of that equation. So that's why it's the null space, because you're solving the homogeneous equation. And again, just a reminder, homogeneous means if you solve for 0. Right?
The eigenspace just like automatically for the zero vector?
It will always, yeah, because the eigenspace includes all the eigenvectors, and 0 will always solve the homogeneous equation.
Oh, right, yeah.
Okay, so let's get at the root of what they're talking about here by doing some examples just to get it into context here. Okay, so with this one, we are showing that -5 is an eigenvalue of that matrix. So what we're saying is that AX equals -5 times X. That is showing that it is an eigenvalue. And so if I take A times X, which let's call it X1, X2, let's see what happens. We get -5 X1 by doing our matrix multiplication, which is row by column. Row by column. So I get 2. Why did I get negative here? Should be 9.
Wait, isn't it 2x1 with 9x2?
Isn't it 2x1?
That's what I meant. Oh, I
So 2x1 plus 7x2 and 7x1 plus 2x2 would equal 5 times x. So if we solve that system, okay, saying 2x1 plus 7x2 equals negative 5x1 and 7x1 plus 2x2 equals negative 5x2, we would find the eigenvector associated with that eigenvalue. Okay, so if I were to do that, then I'll show you another way to do it, because in general I wouldn't do it this way. Okay, so that's from the top. So let's see, I'll probably just, yeah, so you get 7x1 plus 7x2 is 0, and 7x1 plus 7x2 is 0. So in other words, this is going to be the equivalent of having a row of zeros when you row reduce, because if we subtracted these two equations, we get 0 equals 0, which is a true statement. So you have a non-trivial solution, which is required in order to have eigenvalues with their corresponding eigenvectors. So what we can say then is that x1 equals negative x2. And in that, if I were to find my eigenvector, I would do x1, x2 equals, let's say, negative 1, 1, x2, given that relationship. And you could have made either x1 or x2 free. I just decided to make x2 free. So, go ahead. Okay, so I'm just going to back up here. If there is a non-trivial solution to this equation, the non-trivial solutions are the eigenvectors corresponding to that eigenvalue. If it doesn't work, that means it's not an eigenvalue, and it means it doesn't have an eigenvector corresponding with that eigenvalue. Benjamin, hi, right here. Did that answer your question?
Yes.
Okay. So this is your eigenvector. So the corresponding eigenvector is negative 1, 1. And let me just display to you what that means then. What that means is if I, and I'm going to erase this, if I plug in my eigenvector, negative 1, 1 here, what I get is 5, negative 5. And that equals negative 5 times x. Negative 5 times x is equivalent. So in other words, for a specific eigenvector, if I multiply by that eigenvector, it is the same as simply scaling the eigenvector by 5. So it's where matrix multiplication is the same as scalar multiplication, which you know is very rare, that would be the same. Fun?
If you have a whole number involved, will you always have that symmetry there to create in your A matrix to create that kind of value for total? Like if you have different numbers on the bottom and the top, it would create like a fraction or something.
I think so long as you have like this dominating thing.
Yeah, that's what I'm saying. But like if you had 2, 7, 3, 4 or something, you would get like a fraction. Or not a fraction.
No, you should get the same.
Yeah, they don't have to be integer values.
Oh.
I don't think I've answered your question
I don't
correctly,
think
but it
has
can
to
be any value. So let's do it again, but let's do it with a 3 by 3. Okay, so I'm going to show this a little differently, so it's a little more straightforward. That way I was using a lot of non-matrix techniques. Now I'm going to use some matrix techniques to solve. So in this case, I'm solving the equation A minus lambda I times x equals 0. Okay? And that must have a non-trivial solution. If they say it's an eigenvalue, they should say show whether it is. If it's not, okay. So let's calculate A minus alpha I, but in this case alpha is 3, because 3 is our eigenvalue. So I have 6, negative 2, 0, negative 2, 9, 0, 5, 8, 3, minus 3i, which is 3, 0, 0, 0, 3, 0, 0, 0, 3. And I got it's up to you, but that's too tricky. So I'm solving the homogeneous equation then. 3. Here's our homogeneous equation, augmented matrix. I can see I'm going to have a non-trivial solution because I have a row of zeros or a column of zeros. So I'm going to row reduce this. Do you want me to write out the steps? So when I row reduced it, I got 3, negative 2, 0, 0, 1, 0. And then I have my row of zeros at the bottom. So I'm now doubly convinced that I have a non-trivial solution. So with that, with the second row, I get that x2 is 0. With the top row, I get x1 is also 0. Now you might feel a little troubled by that. But what is x3? Anything. So x3 is free. Okay. So x3 is out of the equation altogether, which means it can be anything you want it to be. So the equation, you have x3 free, so we can simply state that it's 0, 0, 1 times x3. So it said find a basis for the corresponding eigenspace. And so the basis is going to be for the eigenvalue 3, the basis is going to include 0, 0, 1 is your basis. Oh. Right. Questions? So that means 3 times our original matrix A is the same, 3 times this eigenvector, 0, 0, 1, is the same as multiplying this entire 1 times 0, 0, 1. So we get a 0 on the top, a 0 for the second one, and then 0, 0, 3. So you can see that that's true by doing a quick matrix multiplication. Yes?
Is the eigenvalue and eigenvector thing used for each matrix A?
So for this particular matrix, it can have different eigenvalues and then different corresponding eigenvectors. So the eigenvalue and the eigenvector are tied together because only one is true with the other. So what we're going to learn how to do is to find the different eigenvalues and then find their corresponding eigenvectors. We've already done the and then, so given the eigenvalue, find the eigenvector, but we're going to learn how to find the eigenvalues in a bit. Yes?
So for this problem, the eigenvector could be like 0, 0, any number.
Yes. Yes, any multiple of that. Other questions? Okay. So this is generally, geometrically, if we're talking about R3, what is happening. So if our eigenvalue is 3, what it means is it takes the vectors, and by multiplying by vector A, multiplication by A, it just scales them by a factor of 3. Notice all the vectors are 3 times as large. So it maps from x to ax by the geometric transformation, dilation by a factor of 3. So it's kind of harking back to, is that the right word, harkening? Back to when we had to describe our matrix, which performed a geometric transformation. This is a geometric transformation, which is multiplication by 3, but it's a lot different of a matrix that we were used to seeing before. Oh, okay. So this is a very cool theorem, and it states if you have a triangular matrix, how you can find the eigenvalues. And it's just super useful. So if you have a triangular matrix that is an upper or a lower triangular matrix, either one. So that means essentially echelon form, if it's the upper triangular and then kind of the reverse in lower triangular. You can simply find the eigenvalues by looking at the diagonal. So for this one, the eigenvalues are 1, 3, and 4. The eigenvalues for this are 1, 0, 6. And if you have a 0 as an eigenvalue, what does that tell you about the matrix? Yes. Well, for that particular eigenvalue, what does it tell you for the matrix as a whole? If you have an eigenvalue of 0.
I don't know if they variable.
Yeah, well, for that particular eigenvalue, that would be true. But for this matrix, what do you know about the matrix? Like not solving AX equals 0. Well, we can look at that too.
Yeah. Anybody?
If AX equals 0x,
No, with you.
Let's look up homogeneous. Let's do like Rn minus 1.
AX would equal 0.
I still use this.
And in order for this to work, this is just the regular homogeneous system, not A minus lambda x, or A minus lambda x. It's just AX equals 0 if your eigenvalue is 0. So if this is true, what do we know about A? And there's a non-trivial solution if it's the eigenvector. So what does that mean about A? Yeah. So I'll just tell you. What's that? Yeah, it's not invertible.
Nice, right? You're genius.
So if AX equals 0, so this is different than A minus alpha I times X. This is just AX equals 0. If you get a non-trivial solution from this, which you should because 0 is an eigenvalue, that means this matrix is not convertible. So if you have 0 as an eigenvalue, that means you have a non-invertible matrix. Okay, so it's kind of circling back to the invertible matrix theorem. The eigenvectors that correspond to distinct eigenvalues will develop a linearly independent set. Okay. Just like the basis of the null space is linearly independent, this is just saying the same thing, but now we're talking about the eigenspace. The vectors that make up the eigenspace are going to be linearly independent. Questions on that?
So what would be a non-distinct eigenvalue?
So, we'll be done shortly. Yeah, you can come in if you want to learn about it.
I don't want to come in. I can sit right here.
Do you guys want to sit or you want to go in the library? It's up to you. Okay.
So what's a non-distinct eigenvalue?
Okay. So there are matrices where you can have two eigenvalues that are, or one eigenvalue that corresponds to two vectors. So like you have an eigenvalue, like let's say you had a triangular matrix and two of the diagonals are both 3. Yeah, those would not be distinct.
And so that would fall linear.
I don't know if the converse is necessarily true, but if they are, I don't believe it is. But if they are distinct, then they'll form a linearly independent set. But I think it can go either way, the other way. Oh, we have no time. Well, this is so cool. It's really quick. Really quick.
Looks like a friend guy.
Steven Stroh, yeah.
This is the guy that tweeted me back.
One of the questions that Doug had asked me to think about before we sat down today was, I suppose you're going to teach a concept in linear algebra called eigenvalues.
There's an eigenvectors, and how would I approach something like that? As I thought about it a little bit before coming into the studio, it fits exactly what you were saying, Edward, that it has a sensory motor side and building up to an abstract side, which is
Anna Vollmer, Tabby Haggett, Abby Schlosser,